Good morning, everybody. Welcome to the fifth and last seminar of the Italy-Germany webinar series dedicated to artificial intelligence. So the seminar series is called Artificial Intelligence Methods and Applications. This webinar is dedicated to AI for medicine. With me, as always, Professor Fiorentini, who is co-organizing this series with me. So this is the second series. Last year we had one on sensors, and next year who knows. And as speakers today, we are happy to have Sara Colantonio from CNR ISTI and Jan EHRHARDT from the University of Lübeck. So I will give the word to Professor Fiorentini, and then I will introduce Sara Colantonio, who will be the first one to speak in alphabetical order. So please, Vincenzo.
Hello, good morning, everybody. So my role here is that of co-organizing with Matteo, who actually did most of the work, and I'm representing the SIGN, that is an association of Italian scientists active in Germany, that is sort of co-organizing, co-participating in the series, and also in a conference that will be held in Villa Vigoni next week. Because of logistics and funding reasons, that conference is by invitation only, but we will be recording the proceedings and so on, make it available to the community that participates in these webinars. Aside from that, I bring the greetings of the Italian Embassy in Berlin. I'm science attaché, one of the two science attachés right now, and I wish you a pleasant couple of talks that I look forward to hearing. Thank you.
Okay, thank you, Vincenzo. Okay, so on the right-hand side, you will have the slides. The speakers were nice enough to send us the slides beforehand, so you can download them and go through them as they speak. As always, so maybe I didn't present myself. Actually, I noticed, so my name is Matteo Pardo. I'm from the International Relations Unit of CNR. I used to be the science attaché before Vincenzo Fiorentini, and I'm still dealing with the German-Italian relations, but now let's say limited to the National Research Council, which I'm representing. All right, so the slides I told you, you can ask questions at the end of both presentations, and you will have to write them down, always on the right-hand side, and then me and Vincenzo will read them to the speakers. So you can also write them down while they speak. We will just read them at the end. Okay, so without further ado, let me present the first speaker, who is Sara Colantonio. I was mentioning that Sara is part of the Institute, is a researcher, senior researcher at the Institute of Information Science and Technology, acronym ISTI, in Pisa. And in particular, she's a member of the Signals and Images Laboratory. And there she coordinates the activities on artificial intelligence for health and well-being. Let's say she coordinated the FP7 project Semioticons, which granted her an award as one of the 40 top transformers in health in 2016. And right now she's a project quality manager of the UH 2020 Pro Cancer Eye, co-leading the working group 3 of this project. And what else? And she also leads the working group Med for Future of the CNR strategic project Foresight. She's a member of the International Multi-Stakeholder Group of Expert Artificial Intelligence for Health Imaging. And there she's contributing to the definition of the future AI guidelines on trustworthy AI in medical applications. So a very big topic of this for the implementation of AI in the real world. There are very many working groups on let's say guidelines for at the end trustworthiness in all various sectors. Right. So please, Sara, it's your turn. I give you the floor.
Thank you very much, Matteo. And actually, you mentioned some of the topics I will be touching upon during my presentation. So I don't know if you let me check.
Yeah, we see your slides.
Okay. In the presentation mode, right?
Yes.
Okay. So good morning also from my side. Thank you very much, actually, Matteo, for the presentation and for the introduction. And of course, for the invitation. It is really a pleasure to be here today and to take part to this really interesting initiative. And before delving into the content of my slides, which as the title suggests, is related to the potential and the challenges of AI in health and well-being, I would like to give you a visual glimpse of the CNR research area in Pisa, and also of my institute, so the Institute of Information Science and Technologies, as Matteo said before, which is located more or less where I place its logo. And actually I have to say that the area is much larger than what you see in the slide, because there are many other buildings that have been cut off from the picture. And this is the largest CNR research area in Italy. And as Matteo was saying, within ISTI, I'm with the Signals and Images Lab, a lab of more than 40 members among research permanent staff and the research fellows and PhD students. And among them, I have the honor and the pleasure to work with a multidisciplinary team of researchers that work in the field of AI and computer vision, with particular focus on their applications to the health and well-being domains. In this respect, the ultimate quest that we are actually pursuing, or at least attempting to push, is the possibility to make it real what in 2019 Eric Topol defined as the high-performance medicine, which is a kind of new paradigm that emerges at the convergence between human and machine intelligence toward the optimization of clinical processes and towards new discoveries that may actually be beneficial for the health and well-being of citizens, but also of clinicians, caregivers, so society at large. And in this field, as the name Signals and Images of our lab may suggest, our activities focus mainly on two fronts. On visual intelligence for supporting the work of clinicians, particularly radiologists, in their diagnostic and prognostic processes based on imaging data such as X-ray, computer tomography, magnetic resonance images, or ultrasounds. And on assistive technologies based on computer physiology aimed at helping people monitor their own well-being. In most of the cases via self-monitoring devices. And today I will spend most of my time on the first area and give you a few details on the most recent activities on the second one. So radiology actually is one of the fields that, as we all know, can benefit the most from the application of artificial intelligence, machine learning, and computer vision techniques. Actually, there are several points where a computerized intervention can be of considerable help to radiologists. I have listed some in the slide. There are, of course, many others, but this one includes the assistance in repetitive and time-consuming tasks, also to improve their reproducibility, especially in stressful and tiring conditions, such as in long work shifts. The prioritization of cases by highlighting those that need more attention by radiologists. And of course, this could be, for instance, really helpful in cancer screening programs where suspicious cases might be prioritized with respect to the others. And also mining imaging data for discovering new diagnostic and prognostic biomarkers, also measuring them in a repeatable way. For instance, to predict the degree of aggressiveness of a malignant tumor. And finally, AI tools may be essential to support centers with limited resources. For example, with techniques that can improve the quality, for instance, the resolution of images acquired via low capacity devices. And to go a little bit more in detail in one of these examples, AI has a big potential in oncological imaging, as it is well known that tumors are characterized by a high degree of heterogeneity. And this heterogeneity has an impact, an important impact on the selection of the best therapy for that specific case. So tumor heterogeneity is due to the genotype, so the gene expression of the tumor, but also to its phenotype, so the specific manifestation of that genotype. And medical imaging is a valuable, non-invasive source of information on tumor phenotype, as it can show morphological but also functional information that stem from this phenotype. And in this frame, AI techniques can help discovering and harnessing this information towards more precise prognostic and therapeutic decisions. Nevertheless, of course, developing effective AI models and systems is not easy at all, as there are many domain-specific challenges and complexities, of course, that affect this domain and that requires ad hoc solutions. And among these challenges, there is for sure the lack of quality and curated data, which is actually a long-standing problem in the biomedical field, though it appears a little bit incredible. I mean, given the amount of data, imaging data that are collected on a daily basis, even in this very precise moment by all the clinical centers. Nonetheless, I mean, structural, administrative, regulatory, and even competitive issues cause that we are always working with limited data sets, which does not allow to develop and test particular complex AI models. Another very important challenge is related to the complexity of the data and the diagnostic processes. Usually, radiologists draw their conclusion by mentally integrating multiple imaging modalities, thus looking at morphological and functional information to detect, for instance, a cancer lesion. So an example that I put in the slide is just the detection of prostate cancer tumor lesions. So there you can see two morphological images, so T2 weighted MRI images. And you can see there are two tumor lesions over there, but of course it's really difficult to detect them. I can help you by putting two arrows that show where the lesions are. But of course, if I also include another modality, which is more functional. Actually, it is a diffusion weighted modalities and the ADC map, which measure the diffusion of water in the tissue, that then the lesion can become more visible somehow, especially, of course, for expert eyes. So the task, as you can understand, is very complex, and it is even more complex if we want to go beyond what the radiologists see to discover new biomarkers. So for instance, to predict the aggressiveness of the tumor that is depicted in this kind of images. Another issue, of course, is the lack of labels and ground truth. For instance, just to stick to the case of the prognostic biomarkers, we would need for predicting and discovering these biomarkers that the tumor lesion is segmented, so is delineated in the slide to compute some computational, morphological, and textural features. However, lesion segmentation is a very time-consuming and tiresome task. Usually radiologists delegate it to residents, and this results in the fact that we have very few annotated data. Another important aspect concerns, of course, the need to deal with the variability of clinical practices, especially in data acquisition protocols, that may vary from one center to another, and may also strongly depend on the vendor or the acquisition device that is being used. Actually, MRI data are strongly dependent on the reconstruction algorithm that is used by the vendor. So one AI model that is applied to data acquired from one vendor can poorly perform on data acquired with another device by another vendor. So delving in more details on the works that we have done so far, I will give you some glimpse on some of the works that we have done. So I'd like to start with an example of AI tool that we have developed for aiding just a burdensome task that radiologist has to address. In particular, to support the work of the radiology unit 2 of Cisanello Hospital in Pisa, we have worked to the identification and quantification of lung tissue affected by idiopathic pulmonary interstitial diseases. So these diseases are rare chronic conditions. You can see some picture on the left of the slides on how it appears in diagnostic high resolution computed tomography images. And this chronic condition may lead to the fibrosis of the tissues of the lungs, causing in the long term a limitation of gas exchange. And in this disease, it is really important to assess the fraction, so the percentage of the lung that is involved by the disease, which means that the tissue should be detected and delineated, and then the interested volume should be estimated, so quantified. Also for understanding how the therapy is performing and if it is really effective. So as you can see in the picture, here, I mean, the disease appears with a specific pattern, which is called usual interstitial pattern, that include diffuse opaque areas distributed in a variable and irregular manner. And this pattern is also called ground glass opacity. To assess the lung involvement, one needs to segment this pattern from high-resolution CT scans. And considering that a CT scan can consist of hundreds of slices, that are images, of course, a manual delimitation of this area is really a prohibitive task. So to automate this pattern segmentation, we have developed a specific encoder-decoder AI model by incorporating in it an attention model and modifying a standard UNet model. So you can see it in the right part of the slide. This is the AI models, and this way we were able to achieve very promising results, so above 86% of the DICE score, even with the small fraction of data that we used. And in this case, the ground truth were provided by the radiologists by refining as a research software that they had in-house. So given the similarities between the WIP pattern and the radiological manifestation of COVID-19, we adopted the same approach to detect and quantify COVID-19 lung involvement. Specifically, in the case of COVID-19, the CT patterns include ground glass opacity. You can see it here on the left of the slides, ground glass opacity, but also consolidations, which refers to areas of the lung tissue that is normally compressible, but with COVID become filled of fluid instead of air. So to segment both ground glass and consolidation, we adopted the approach that you can see on the right part of the slide. So we trained again an attention unit and compared its results with a simple unit and also a recursive unit both with and without attention, showing that the attention mechanism alone is able to achieve the best results, both in terms of DICE and in BF scores, as you can see in the table in the slide. In this case, the ground truth was obtained as a manual refinement by expert radiologists of the initial segmentation that we provided by our WIP network that I presented before. And to further improve these results, we focused on multimodal segmentation to deliver a model able to distinguish between the ground glass opacity and the consolidation pattern. So an accurate segmentation of consolidation is actually a particularly difficult task, as they usually appear very similar to the tissue around the lungs and chest, and are easily excluded from the segmentation. So to overcome this problem, we further modify the attention unit by incorporating an anatomical prior. You can see it here in the slide. As within, the skip connection of the UNET model to more precisely guide the attention mechanism of the net. And this actually resulted in an improvement in the performance of the network, which is even much better than applying just a first pre-processing step based on lung segmentation. Moving to an example related to oncology, we have been working on estimating the aggressiveness of prostate cancer. So just the difficult example I was talking you about before. And this is actually a very cogent clinical question, as prostate cancer is the second leading cause of death in the male population. On the left side of the slides, you can see the clinical diagnostic process that is currently followed, of course, which involves as a first step a multiparametric MRI examination, which is qualitatively evaluated by radiologists according to the so-called PIRAD standard. And based on the PIRAD's evaluation, the imaging exams is followed by a biopsy. You can see a sketch of it in the slide, which is actually an invasive and very annoying procedure, but is currently the only procedure that allows to assess the aggressiveness degree of the lesion. In this context, in collaboration with another institute of CNR, the Institute of Applied Physics in Florence, and also with the Careggi Hospital, always in Florence, we have developed an attention-based convolutional neural network trained to predict tumor aggressiveness. So you see the sketch of the architecture on the right part of the slide, thus allowing to implement in this way a kind of virtual biopsy that may identify the real clinical significant tumors that need to be further investigated via biopsy. And we compare this model with a model without the attention, and actually showing that the attention mechanism does indeed help the prediction, as you can see with the performance result in the table. And we moved even further the use of the attention mechanism by training a 3D vision transformer, which is in the bottom part of the right box of the slide, by training it on a publicly available dataset, prosthetics, and by defining a specific 3D attention mechanism. And this way we obtain interesting results, even though they are still limited, as the data actually are still very few. Considering instead low resource settings, another solution that we have been working on involves the assessment of hepatic steatosis, commonly known as fatty liver, which is a disease caused by the accumulation of fat on the liver tissue. And early diagnosis and accurate quantification of steatosis is essential to prevent much more serious diseases that may be the cause of much serious condition, mainly related to cardiovascular diseases. And currently, steatosis is assessed using invasive but unreliable techniques. You can see a picture in the slide on the left part of the slide, which is actually biopsy. So by sampling some tissue in different position of the liver. Or it is assessed with a more reliable but actually more expensive and poorly available device, such as magnetic resonance spectroscopy or elastography. So in collaboration with the University Hospital of Pisa and the CNR spin-off KIPU, we have developed a simple regression convolutional model capable of estimating liver fat content from a much less invasive protocol, which was developed by KIPU, for acquiring actually ultrasound liver clips, so small videos. And these protocols defined by KIPU ensures and guarantees that the acquisition ultrasound data are actually homogeneous and acquired in the same manner. So the model that we have developed was trained on data from 2 clinical centers in Pisa and Naples, and using as ground truth the fat fraction obtained from the MRI spectroscopy. So by analyzing these ultrasound clips, such a model is able to predict the percentage of fat measured by spectroscopy with an average error of just around 1. So, however, I have to say that the cases that I've shown so far, though they appear promising, are in any case still research endeavors. And this is the case for many of the work that are being published, that have been published so far in the literature, or that have been even advertised on the news. Actually, there is still a significant gap between research and clinical practice. For example, according to the American College of Radiology, there are currently 238 approved software products in radiology, but all 24 of these are really meant to support the diagnostic process. So they incorporate some automatic image processing algorithms. The rest are mainly archiving systems. Moreover, a recent survey carried out in Australia and New Zealand found that more than the 80% of clinicians do not use any AI-based systems in their routine workflows. And the same, of course, is true for other Western countries. So the reasons for the limited routine adoption are many, and they might be grouped at a technical level, where one of the main challenge is the limited generalization capacity of AI models, which are developed so far on small data set and are validated on small internal subset of these, as the example that actually I showed you. And these data sets may be not representative of the larger and more diverse population of patients. And additionally, there is, of course, a lack of standardized reporting and evaluation procedures of AI models, which make it hard to compare and assess their performance and reliability. Other challenges are more at the human, the organizational level, where the main challenge is actually the trust and the acceptance of these AI tools by radiologists and other stakeholders. And so prospective randomized control trials are needed and may serve this scope by showing the clinical utility and safety of AI applications, but there is a general call for more transparency and openness of AI models, as this can actually help to build trust and confidence in their decisions. And of course, there is still this big open question about the liability and responsibility when AI models are used for diagnostic purposes in practice. So in this respect, we are lucky to be partners in some important national and international initiatives, which are aimed at creating the substrate and the infrastructure to foster the transition of AI in radiology from research to clinical practice. These are the European H2020 project ProCancerAI that Matteo was mentioning at the beginning, the Tuscany Region Project Navigator, and also the European project EUCAIM, which has been launched just at the beginning of this year as the flagship project of the Europe's Beating Cancer initiative in the case of medical imaging. And all these 3 projects involve the collection and the storage of large amounts of imaging and clinical data from different clinical centers. In the case of ProCancer Eye, we are talking about 17,000 cases of prostate cancer, and of course multi-parametric MRI imaging data, while for Navigator the figures are of course smaller. This is a regional project, but still significant, as we are talking about 1,500 cases for prostate, rectal and stomach cancer. And the EHRHARDT is the largest one of the 3, and it plans to collect 60 million images for about 100,000 patients all over Europe. So all these 3, all the 3 projects provide platforms for hand-to-hand development of AI models in order to to meet the principles of trustworthiness and transparency, as well the mandates of open science and of the AI Act by the European Commission. So delving in a little bit more detail into the ProCancer Eye activities, the project involves 13 clinical centers collecting retrospective and prospective data with their ground truth and contextual clinical data. And this data serve the training of AI models addressing 9 use cases. You see them in the slide here. Which cover the whole prostate cancer continuum, from detection to aggressiveness prediction, metastasis identification, and also best therapy planning. And the project has currently collected nearly 9,000 retrospective cases for more than 18,000 imaging data points, and has just started with the collection of prospective data, which are already more than 1,000. So the AI approach of the project comprised the delivery of one master model trained on the whole data set, and by using all the retrospective data acquired at different time points according to different standards, so different version of the PIRAT standards, and with different vendors. And this model is meant to act as a sort of baseline to then develop vendor-specific and vendor-neutral models, so models that are able to overcome the limitation I was talking you before, so about the generalizability of AI performance on data acquired with diverse vendors. So in some way, the idea behind this master model goes in the direction of the emerging trend of devising foundational models, in this case specifically for medical imaging and prostate cancer, which may be used for fine-tuning or transfer learning on different use cases, on different data acquisition protocols. And this is what we are about to do by using self-supervised training approaches. And ProCancer Eye is also important as it is one of the 5 flagship projects, and you can see their logo in the slide. They are European Image, PrimeAge, Incisive, and Chameleon, which has created the AI for HI, so artificial intelligence for health imaging initiative, which is at the basis of the EHRHARDT project. One of the first important results of this initiative has been the definition of the so-called future AI guidelines, which are meant to aid and facilitate the work of AI developers in the biomedical field towards the deliverable, of course, of reliable and robust solutions. And the guidelines were initially prepared by a group of members of the 5 projects, and then were modified based on the feedback obtained from a large group of international stakeholders. And the guidelines promote mainly 6 principles. You can see them in the slide, along with the relevant literature paper justifying the need for that principle. So they include fairness, which stands for the need for equitable systems that do not promote any kind of discrimination. So probably properly perform on underrepresented subgroups of the population, or at least make stakeholders well aware of their limitation in this respect. Universality, which mandates for systems that are based on standard and verifiable approaches and that can also be easily exported in limited resource settings. Traceability, which demands for transparent and traceable systems whose details are tracked and well documented, both in their development life cycle, but also after their deployment. And actually, this is because we are all well aware that learning-based algorithms suffer of different types of drift when they are deployed in production. So in this respect, the traceability principle mandates to monitor the AI performance also after deployment to detect whether the models are actually performing as they are expected to do. The usability principle requires, of course, that the AI systems really fit naturally in the diagnostic and clinical workflow, and so requires that actually stakeholders and end user are directly involved in the co-creation processes of the AI models. Robustness, of course, mandates for systems that are capable of generalizing and managing also adverse conditions and adverse situations. And finally, explainability requires that the AI system actually provide end users with the necessary elements to let them make a safe and suitable use of the prediction the same AI models provide them with. So the guidelines provide a list of the recommendations. I've included in the slides and some example of just a screenshot of the table that is included in the paper, which is actually under review for the Lancet Digital Health journal. So considering the future AI guidelines within ProCancer and in collaboration with the Candiolo Clinical Center, we have designed a questionnaire to understand the minimum requirements that an AI model must meet to be considered reliable in clinical practices by clinical users. And we have circulated this questionnaire initially among the clinical partners of ProCancer, and according to their initial feedback, we have revised it and now are circulating it among the members of the European Society of Oncology Imaging. So from ProCancer, we collected 38 replies, and we analyzed them to steer our activity within the project. But in the slide, you can see some charts which show you the profiles of the responders, which could be summarized as an over 35 European radiologists working in a public hospital, mostly specialized in abdominal imaging with basic knowledge of AI. And according to this reply, we have drawn some conclusion that I'm showing here in the slide, as they might have some general interest for the audience. So among the various reading modalities, for sure what we understood is that the rule out ones is the less desired and actually also objected by clinicians. Actually, these modalities encompasses that the cases that are considered normal, negative, or benign by the AI models are actually ruled out for their examination. So they are discarded from their examination and the clinicians have no look at them. And this, of course, is not at all appreciated by clinicians. Among the features that an AI system should exhibit to be considered trustworthy, what we found out is that all the options that we provided were well received, but there was a preference for reliability, so high accuracy mainly, for the certification and the transparency of the AI models, which should also consist in the documentation of the data and the characteristics of the data used to train the AI models. And finally, we found out that there is a strong demand for having the output of the model coupled with a kind of certainty or confidence score by the AI model, which would also send an alert and so highlight when it is not sure of the output it is providing. So besides this questionnaire and beside defining the guidelines, we are also working to develop methods that may support the compliance with the future AI guidelines. So as far as traceability is concerned, we are collaborating with EHRHRDT to define the so-called AI model passport, which is meant to be a tool to automatically check all the relevant pieces of information about the whole development life cycle of an AI model. So you see the different phases of this life cycle in the slide. So starting from data collection to the deployment in production of the model. And this passport is mainly a metadata format that stems from previous works on provenance or reproducibility, such as W3C ProvML and ML schema or Google Model Card, but it is much more comprehensive and it is automatically integrated with tools such as DVC for data versioning, MLflow for AI model development, and also for Mini.io for the interface rendering. And besides the computer readable version of such a passport, we are also working to render the passport in a human readable format. You can see it in the slide, which might be actually useful also as a device history log that might be used for device clearance by some certification bodies. With regard to robustness, since as we have seen also from the results of the questionnaire, it is really important to provide the end users with an estimate of the reliability and confidence of the prediction, we have started to prepare a library of methods for estimating the uncertainty of AI models. And we are doing this by integrated mostly post-hoc methods, so which are methods that could be applied to already trained AI models to estimate the uncertainty of their prediction. And this includes the so-called trust score, which is based on the training of a simple classifier and use this classifier to verify the trustworthiness of the initial one, and the topological uncertainty, which is based instead on the analysis of the topological features of the activation map of the network. As far as explainability is concerned, considering that clinicians often evaluate a case at hand based on the similarities this case has with previous cases they have already seen, we work to verify the efficacy of a particular network, which is called ProtoPNet, which uses state-of-the-art convolutional neural network to prototypical part learning, which means to learn prototypes or part of prototypes that can be actually used in a similar way to clinicians' case-based reasoning. And we applied this network to the prediction of breast cancer malignancy in mammography examinations and had the results evaluated also by an expert radiologist to evaluate the goodness and effectiveness of the detected prototypes, the learned prototypes, and so the explanation provided based on similarities. So in this slide, you can see how the network works. So for any new case, the inference is based on the detection of, on the discovery of part of the in this case, the breast tumor, that are similar to the prototypes that have been learned by the network. So the final inference is given based on the higher similarities values with the prototypes of the corresponding class. And the performance results we obtain are not particularly high, as you can see in the table in the slide, but the experiment we did with clinicians showed that the discovered prototypes made actually sense for them, especially in the case of malignant cases. So moving quickly to the assistive technology part, we have recently worked to define a cardiometabolic risk model for predicting the risk of cardiovascular disease or type 2 diabetes. And this model was defined based on the parameters obtained from a self-monitoring device, which looks like a mirror. You see it in the slide, and which is able to estimate parameters such as heart rate, fat mass, accumulation of specific substances in the skin, and stress condition from facial analysis. And using the data collected, I'm just finished, just 2 slides and another one, and I finished. Matteo?
Okay.
Using the information collected by the mirror, we developed an AI model based on structural equation and self-organizing maps to estimate the well-being index. So also in this case, of course, the case of assistive technologies, several are the concerns that prevent their acceptance and uptake in real-world practices. And within the Cost Action Good Brother, we set a multidisciplinary debate aimed at defining the guidelines for overcoming these concerns. So you see a couple of them in the slides, but actually you can go to the project website and have a look to all the list of guidelines. And we are actually defining the technological mean to comply with these guidelines. So, and this was actually my last slide. So I stop here. Apologize for taking longer.
No, it's perfect. Perfect. Okay, thank you very much, Sara. And I have a few questions, but as the other ones, I will ask at the end. So please, Vincenzo.
Sorry, yes. Okay, so now we move to the second talk. So the talk is by Jan EHRHARDT. Jan is computer science at the University of Lübeck.
Sentiamo malissimo, Vincenzo.
Ah?
Sentiamo malissimo.
Yes. Better now?
Maybe. Try.
Better now?
Yes.
Hopefully.
Yes. Now it's better.
Oh. Com'è adesso?
Meglio, meglio, così va bene.
Okay, I'm sorry. Sorry about that. So our next talk is by Jan EHRHARDT, who holds a PhD in computer science from the University of Lübeck and has done postdoctoral work at the University Medical Center in Hamburg, and is now a senior research scientist at the Institute of Medical Informatics at the University of Lübeck. He's an expert in learning-based method in multidimensional medical imaging, and so he focuses on machine learning methods to model dynamics of pathological processes in the human body. And so, not surprisingly, his title has to do with medical images, and it's learning disentangled representations of medical images for population analysis in medical application. Please, Jan.
Okay, thank you very much for the nice introduction. I hope everybody can hear me. Is it okay?
Yes.
Sound is good? Very good. Okay, thank you for the nice introduction and for the invitation for this talk. And I'm have a long title here, and my talk is a bit more in-depth for a specific topic, the disentanglement. As you have seen on the first slide, I'm associated with the Institute of Medical Informatics and also with the a German research center for artificial intelligence as well. And both are in Lübeck in the northern of Germany. And both are led by Professor Heinz Handels. And so there's a close cooperation between the two institutions. And we have a very long-ranging competency in different methods for medical image analysis and in machine learning, but as well as in conventional or classical methods like optimization-based methods for registration or segmentation. And we're also working on the combination of images with clinical parameters. And the tasks we solve are very diverse in the field of medical imaging. For we apply methods for image segmentation, registration, visualization. We have done much work in the area of the analysis of temporal images, and we also try to generate diagnosis or prediction supporting systems. And the goal, and that's more on the side on the German Research Center, is to develop task-specific approaches for specific medical applications. And the main goal of all this work is to reduce the manual effort for the medicine or for the physicians. Okay, I will start with a few slides about machine learning in medical image analysis in general. And this is quite short. First of all, the medical image analysis field is very diverse. So as mentioned also in the talk before, we have a large number of imaging techniques and different imaging devices as well. And you can see on the right side a few examples for mammography, MR images, CT, X-rays, histopathological images, and so on. And the applications in our field are as well as diverse as the diseases in the human body or as the pathologies in the human body are. And in the last years or over the whole course of the last 30 years is the number of image examinations in healthcare growing. You can see in the charts the number of MRI scans acquired in Germany during the last 10 years. And you can imagine that the manual examination of all these images is not possible for the physicians, and we need some automatic support for this. And here deep learning has achieved state-of-the-art results in many, and in my opinion, most medical imaging applications today. So the tasks we address with machine learning and medical image analysis are very diverse, nearly all you can imagine. Yes, so we have classification tests, tasks to decide is it a tumor or not. We have detection tasks you can see on the upper right side, the detection of lung nodules and CT scans, segmentation tasks to find the shape of specific organs in the image to as basis for further analysis, like measuring volumes and shapes and so on. Registration can be supported by machine learning. Diffusion of images is shown on the lower right. You see the fusion of MRI, CT, and PET image enhancement for artifact reduction in CT. In image reconstruction, machine learning is used. Synthetic image generation for education purposes or for training of networks is also a topic. And I think I forget some of other topics to mention here on this slide. Okay, in my talk today, I will not speak about all these topics. I'm more concentrated on a few specific topics we worked on in the last years. And as task, I selected two for this talk. So one is the segmentation of brain MRI images. And you can see on the top of the right side the T1 weighted MR images of different patients. And we want to segment the different anatomical and functional areas in the brain. And this segmentation is the first step for many applications in neuroscience. For instance, the diagnosis or the image-based diagnosis of neurological disorders is based on such segmentations, for instance, for Parkinson or Alzheimer. And a more concrete is the second topic, the image-based detection of Alzheimer's diseases. So Alzheimer's disease is characterized by an atrophy in specific regions of the brain, and we can detect Alzheimer's disease quite early with MRI images if we analyze the size of the specific brain structures. And to do this, we have to detect the differences between what is the normal size of a specific structure for a given age and what is a disease related. So we have to decide, is it the normal appearance or is it a disease related? No, that's a base. Okay, I will come back to both tasks in my further talk. But first I want to introduce one of the terms in my title, the term disentanglement. And to motivate this term is, to motivate this, I show you a T1 rated MR image of one subject. And the question is now, what are the factors that compose this image? So what do we see in this image? And of course, there are on one side the subject-related factors. So we see the individual anatomy or morphology of the patient, and also some tissue properties specific for this patient, like how many fat or water is in the tissue or what is the structure. And also we see some specific properties like what is the age of the patient, what's the sex, weight, health conditions, because these conditions influence how the morphology and the tissue properties of this specific patient are, also pathologies. But we also see acquisition, more technical or acquisition related factors. Of course, the modality, we see it's a T1 rated image, so we see only specific properties of the tissue. But also the concrete device used to measure this image and what are the concrete parameters we have selected for this image. And the third component is also that we see some stochastic effects like different types of noise and quantization errors. Okay, in most cases we are interested in the subject-related factors, and we want to be as agnostic as possible from the technical and stochastic factors. That's the point. But we have, at least if we want to process large amounts of images, we have a mixed data pool in nearly all of our tasks we try to solve. So we have different subjects, but also different acquisition techniques, or at least different acquisition devices. So on the left side, you see images from a project that is related to the detection of Alzheimer's disease, and you see T1 rated images from different subjects, and you can see the shape of the structures differs for each subject, but also these are acquired from different devices, and now it's difficult to decide is the intensity shown dependent on the specific subject or on the specific device. And on the right side, you see images from a project that tries to solve the brain tumor segmentation task. And we have again different patients, but also not only different devices, but different modalities, so different MR protocols used here. And we see different intensities. The term disentanglement is now, or the intuitive definition found in one of the recent papers was we want to separate out the main factors of variation in our data distribution. And in a way that if we intervene one of this factor, or if we change one of this factor, then we get also a specific change in the generated data. So we want to disentangle factors that have a specific influence on the generated of the data we have. And if we have such a disentangled representation, then we can use these to increase the robustness of tasks we do after this, of the downstream task. And this helps to get more modality independent, noise agnostic, more maybe also independent on pathologies and so on. And we can also use this to synthesize images with specific properties. And it also, this was also mentioned in the talk before, the explainability. We can increase the interpretability of downstream tasks because we can now see what factors are used by the decision process, and we can check the plausibility of this. Good. On this slide, I only want to talk about the setting I have in mind during the course of my talk. So we have a network function, and the network function gets an input, and in our case, the input is an image, and produces an output. And the output can be an image or a segmentation mask or a classification result and so on. And internally, the network function is composed of an encoder that takes the input and produces a latent representation, and a decoder that uses the latent representation to produce the output. And the latent representation in the disentanglement setting should be separated in factors that are relevant for our task and other factors that are not relevant or should be ignored by our task. This is the main idea of disentanglement, and most network functions do this in some way, but I will be more specific now. And the question is now, how can we learn such a good representation set? And good means, in our case, a disentangled representation. And a good idea would be, we just take our network, we put in amounts of data, and then we get a good representation. But unfortunately, this is not the case. So this unsupervised disentanglement, so disentanglement by just putting in the data, is fundamentally impossible without using any inductive bias on both the models and the data. And this is here, the citation to this is very new, is quite new, but this goes back to research from the 90s that we know unsupervised learning of disentanglement is not possible. And therefore, if we want to learn disentanglement, we need supervision, so labeled data, the factors we want to disentangle labeled, or we have to use this inductive bias by bringing in domain-specific knowledge into the design of the networks or the design of the loss functions, or both by performing the data pre-processing or augmentation, or even in the data selection. So how can we? So we can learn supervised. We can learn disentanglement in an unsupervised way, but we need specific designs of the network architecture, or we need specific pre-processing or augmentation of the data. And I show here three main network architectures used for disentanglement, and I restrict myself here to generative models. And I'm assuming most of you are familiar with these models. On the top left is a variational autoencoder. The idea is we have an input image X, and an encoder produces a latent representation Z, and the decoder try to reconstruct the input image from the latent representation. And we can make some constraints on the latent representation. Maybe we say that it should be a normal distribution with conditional independent latent variables. So this, but we can also make more complex restrictions on our latent space. The second model on the top right is in conditional GAN. So we have a latent representation, a generator that produces an image, and a discriminator that compares the produced or that justifies if the generated images is very similar to real images, yes or no. And we can learn this, and we can add an additional condition to the generator, and then we have a conditional GAN. And in the lower left, there is invertible normalizing flows. There we have an input network that projects the input on the latent representation, and this network is invertible, so we can go back from the latent representation to the input, and so we can adjust. The data distribution of the input images project to a distribution that we want to, maybe a Gaussian distribution. So these architectures can be all trained in an unsupervised way, but we can also add additional constraints to train it in a supervised way as well. And I will show in the following a few projects from the last years where all of these architectures were used. And I start with a supervised disentanglement, and here in the concrete case for the synthesizing pathological images. And for this project, I come back to the first task I mentioned, the segmentation of brain MRI. And for this task, there is a long history of research in this task, and there exist very accurate methods if the images are from healthy subjects and are from T1 MRI and of modality T1 MRI. But it's more difficult to get an accurate segmentation if we have pathologies in these images or we have another modality or both. And to develop methods that are able to produce accurate segmentations for pathological images, we have to train this method, but the problem is now, how do we get the ground truths for training? And that's the goal of the project we have. How can we train such networks without a given ground truths? And the situation is as following, that we have a large amount of images that are segmented with the anatomical structures for healthy subjects from the T1 domain. And we have pathological images from the T2 domain. And in these pathological images, we can segment the pathological structures as well. But for the training, we want to generate realistic pathological data that have labels for the pathology, but also for the anatomical structures. And if we can synthesize these images, then we can use this for training of a network that can segment the anatomical structures in pathological images. And the approach we used here is a disentanglement approach as well. And we try to disentangle the morphology and the appearance. So the morphology is the topology, the shape of the structures, and how they appear with intensities in the images. And the idea is to use sketches or extract edges from the images, and these edges represent the morphology without any intensity. And then we learn a network that generates from the edges an image, a realistic looking image. And we also add a tumor map for the pathology. And we train this network, in our case in conditional GAN, we train this network on the domain of the pathological data, so with the given pathological data. And if this model is trained, then we can apply this model to sketches acquired or generated from the healthy images of the T1 domain, and this will then, and the network will produce realistic looking images of the T2 domain with the inserted pathology, but with the morphology of the healthy subject. And because we keep the morphology, we can use the labels present in the healthy data also for the generated pathological data. That's the main idea. And in this idea, we use a condition again, as mentioned before. And the edge map is used as a condition for the GAN. And this condition is, or this edge map is shape representation in our case. And the random input of the generator from the GAN model is the appearance representation only now. This trained that the appearance is taken from the set distribution, but the shape is given by the condition. And from this generated network, from the scan, from the generator, we get an image with a tumor inside, but it's not fully realistic at this point because tumors also make some deformation on the images as well. And we have trained also a model that learned these deformation and can apply this deformation now to the image. And we combine all this with the ground truth annotations we have from the healthy data and from the pathological data, and generate synthetic data with ground truths. And this is shown here on the bottom. On the left, two images are real T2 images. Then there is a T1 image with a specific morphology. And we can keep this morphology and add different types of tumors inside, so to generate synthetic data with the same morphology as the T1 data, so with the same anatomical labels. And these images can be used to learn a segmentation network, and this is what we have done. And we can see that the synthetic images have the potential to increase segmentation performance on real pathological data for this segmentation task. Yeah. Okay, this was one example for supervised disentanglement, and in the next part of my talk, I will speak about unsupervised disentanglement, and the application is in the area of population-based analysis. So the idea of population-based analysis is we have a large amount of images and we want to analyze what are the variations in these populations of images. And these to analyze, or the goal by analyzing the variations is to detect some disease-related deviations or to model some physiological processes, for instance, aging. And another point we can do by is if you have analyzed the variations in a real population, then we can use this information as well to generate more realistic synthetic images. But the variations we see in these images are related to different underlying factors. So one, of course, is the morphology of the subjects. But we also see some device-specific factors that are in our population, and we are only interested in some of these factors. In most cases, only, for instance, in the morphology, and we don't want to model device differences in our analysis. So in the concrete case here, we are interested in the disentanglement of appearance and shape. So our main focus is on the morphology. So what is the shape of the organs and structures? What is a normal shape? What is a normal deviation from within the normal? What is the deviation within the normal range? And what is the deviation for pathological ranges? And so we make a disentanglement of the shape that are what we are interested in, and the appearance. That's all the rest to say. Good. And as learned before, if you want to do this in an unsupervised way, we have to apply some sort of assumptions, an inductive bias. And our assumption is that our images are composed as an average normal anatomy. So what is a normal anatomy? Plus intensity changes that are specific for the subject or the used device, and a deformation that describes the morphology. So in the deformation, we code the morphological information by warping the template to the concrete shape of the patient or of the subject seen here. So that's the model we use for our disentanglement approach. The problem is now that the disentanglement of shape and appearance is ambiguous. You can see on the right top that we can simple models, or we can simply generate the input image by using the templates, the normal anatomy, plus an intensity offset without any deformation, by just introducing all missing intensities in the input image in our appearance. But this is certainly not what we want, because in the appearance now new structures are introduced that are not present in the template. And what we want is shown on the lower right side, that our appearance only changes the structures that are already present in the template, but will introduce new structures in the image. So we have structures, and we want to deform these structures so that the shape of the subject is reached. In our approach to solve this, so how we add more constraints to have a well-defined problem, is to use a metamorphic autoencoder, and we introduce into the autoencoder a guided filtering layer, so a special layer that prevents the appearance map from introducing new structures. I don't want to go into detail about the filtering approach, but it's a layer that prevents the appearance to generate structures that are not present in the template. So our network structure in this case looks in this way. So we have more or less a normal autoencoder structure. So on the left side, you see the input image, then the encoder will generate a latent representation, and the latent representation is divided into two parts. The upper part, the red one, is used by an encoder to generate the appearance component, and the lower part, the green one, is used by decoder, again by decoder, to generate the deformation. And also, we learned during the training set from the population of images the template. So the template is normally learned from the population, and we assume that our input image can be reconstructed by a template plus appearance map and an additional deformation. And this autoencoder is trained in a way. If we do this, then we have a disentanglement of appearance and shape. And you can see here on the top row and appearance interpolation. So we have on the left side source image, and we want to produce an image that has the appearance of the target, but the shape of the source. And this is done in the top row by an interpolation process is shown here. So on the right, on the top row, you can see the result. The image has the same shape as the source, but the intensities of the target. And in the bottom row, we do the other way. We want to have the intensities of the source, but the shape of the target. And this is an interpolation only in the shape space, or the shape part of our latent representation. You can see the intensity is kept, but the shape of the structure changes towards the target. Okay, how can this help in population studies? So the main idea is we have a bunch of images, and we use these images to learn a global template. And then we have a template that represents the average anatomy in our population. And we can use this average anatomy maybe to define structures of interest in our average template. And then we map the template back to the original images. And in this way, we can deform our template and also the structures of interest. So we adapt the structures of interest to the subject-specific anatomy, in this case, some subject-specific shape. And this is shown here in the video on the right side, that we have the template and we make this interpolation to be more visually pleasant. For each subject we have. Yeah, we see that we adapt shape and appearance here for this video, but that's not necessary for our application. So, and then we have a subject-specific shape, so it's something like an automatic segmentation method, and we can analyze how the shapes changes between different subjects, and if we project this over the age, then we get a decrease of the different structures or different decreases of different structures in the brain. And this is this shows the aging process in the brain here. And the good thing now is that we can use our approach also to be more modality independent, so we can use it for different modalities as well. So if we have in our population different modalities, the same model will work too. Okay, then I have a part, but I think I will skip this due to reasons of the time. We can do an additional step. We can also try to disentangle the normal appearance from pathological parts that we see in some of the images. And the main idea is to use such a 3-head decoder. But again, the problem appears that we need additional constraints. So we have to make assumptions to be able to make a disentanglement in an unsupervised way. And here we make a special assumption, the low rank and sparse constraint, but I don't want to go into detail here due to reasons of time. What we get in the end is a fully unsupervised approach that is able to disentangle the shapes, appearance, and pathology. And it's an autoencoder model, so our reconstruction quality is good, but not as good as again model I presented before. And we can use this to support downstream tasks. I will see it in a few slides. And so to show one other application is we can use a model for instance, for unsupervised pathology segmentation. If we can decompose our image in the normal part, the normal shape, and the pathology part, then we can use the pathology part here combined with an automatic segmentation method that with a classical automatic, with a more or less threshold-based segmentation method, and we get quite good results. So we have an unsupervised pathology segmentation method as side effect. Okay, that's the last application I want to show, and this presents work in progress, so I end in the middle somehow. And again, I go back to the task of the image-based detection of Alzheimer's disease. And as said before, to detect, or the goal is to detect Alzheimer's disease as early as possible. And to do this, we have to detect the gap between what is a normal atrophy of brain regions due to the age and what is disease-related atrophy of some brain regions. And so we have to detect this gap. And to be able to detect this gap, we need something of a model what is the normal for aging process. So what in the first step is normal? We have to define this somehow. And to do this, we use again a disentanglement approach here. And the idea is we have a population of images, quite large, because there is a large study that acquired images exactly for this purpose. And for these images, we have given the age. And then we use some sort of pre-trained encoder that projects the images to a latent shape representation. Yeah, the representation of shape. We are only interested in the size of the structure, so only in the morphology. And this latent shape representation can maybe be or comes from the autoencoder I showed you before. Yeah, it's only the shape part. And then we use an invertible flow network to project this representation of shape in the middle to the representation of shape on the right side. And in the right side, we have a specific factor disentangled, the H. And we do this in a supervised way by saying that this disentangled factors should be as close as possible to the real H of the input. And then we have a disentangled representation where H is independent, is one factor, and all other factors that that specify the morphology of the plane are independent of this. That's our model we use here. Okay, and if we have learned this representation, you have to keep in mind we can go in both directions with the interpretable flow. So we can again use for a given H representation, we can generate the latent space representation that were used in the autoencoder, and we can then apply the decoder to generate the image again. And using this model, we can generate something like an average brain, but now not only the average from the population, but all for specific ages. So we can show what is the average image for a specific age in our population. That is one point. And the other one point is that this method also delivers so-called attribution maps. And these attribution maps show the regions where age-related effects are very prominent. So also show the influence of the age variable on specific regions in the images. And these attribution maps can now be used to justify the plausibility, or to look at the plausibility of the model. So is it plausible what the model says, that age effects are mainly prominent near the ventricles? And we can say yes, that's very plausible. That's one point. And the other point is also coming back to the last talk. Sara talked about individual medicine, the precision medicine per individuum. We can also use this model to make predictions for a specific subject. So we have here shown the input image for a subject with age 51, and we can use the model to make now prediction how will this brain look for age 61, 71, 81. And if our population only contains normal images, then we have a model of the normal aging process for this specific subject. Okay, also forget to mention that, of course, this model can also be used for age prediction. So we can only put in an image and the model predicts an age, and we looked what is the average error, and we have an error of 4.5 years for the age prediction task. That's okay. Good. So I'm nearly at the end of my talk. I talked about disentanglement or disentangled representation learning in medical imaging or in the medical image analysis domain. And one point is that we can use disentanglement approaches to introduce the domain knowledge in different deep learning settings. So we can introduce the expert knowledge somehow in the design of the network structures, in the design of the loss functions, or in a supervised way. So we have an unsupervised and unsupervised way. And disentanglement is also a good way to increase the interpretability, to overcome the black box character of our decision task, and to increase the robustness. And at the same time, we decrease the complexity of downstream tasks by knowing what factors do we have to use by our downstream task. And this enables the synthesizing of images with specific properties, as shown in the first example. And I discussed in my talk some example applications, and with different network architectures used. These are the main architectures used in the disentanglement learning. And I have also showed applications for supervised and unsupervised approaches. Okay, that's the end of my talk, and I thank you for your attention.
Okay, thank you very much, Jan. Now we would go to the questions. I'm just seeing that I don't see the question tab on the right. Vincenzo, do you see it? Valentina, are you there in the background?
Yes.
Non vedo le domande.
Oh, sorry.
Ah, ecco, adesso sì. Now I see them. All right. So if you want to ask, probably until now you couldn't, I don't know. But if you want to ask questions, then write them down on the right-hand side. All right. So let me begin then, because there are no questions yet. I guess that possibility was not there. So my question is for Sara, and you spoke, maybe I missed something, but you spoke of attention-based models. I don't know what they are. So maybe can you explain what those the main features of those models?
Yes, sure. Attention-based models are convolutional neural net models, so deep learning models that use this mechanism, which is called attention, to focalize their, processing to enhance and make them more focus more, let's say, on specific areas of the images that they process. Okay, and so in this case, in the first case, for instance, that I've shown, so talking about the segmentation of interstitial lung diseases, the attention guided the network to focalize on specific patterns. So you just sum to the convolution that the network does additional information that is, let's say, carried in the different layers to enhance some features. So it's an inner structure of the network that make more evidence the relevant parts. And this mechanism is also learned by the network. So according to the task that the network has to accomplish, it learns how to enhance the relevant information and to accomplish, of course, that task. So it's an inner structure of the model.
It's a first step that you can somehow learn from the data.
You have all along the training, all along the architecture, and all along the training process.
Okay, so I cannot imagine how it's done, but
it's a mathematical mechanism, and it is actually at the base of, for instance, we all know about ChatGPT-3 and GPT. So they are text transformers, and they use this attention model, this attention mechanism to focus on which are the relevant token that is using in the sentence. So the attention mechanism takes along the processing the most relevant information, but it is just a mathematical construct, let's say, that inside the architecture. So you usually perform convolutions or feature extraction. In this case, you also add this information about the relevance of the of some part of the input data.
Okay. Right. Okay. Okay. Then you spoke about a big projects where you analyze a lot of retrospective data. I think it was the
cancer, yes.
Pro-cancer. So do you have ways to do a quality control, because you have data from various sources, right? So do you have a stage of quality control somehow?
We are actually doing the quality control now. At the beginning, what we have done was to ask the clinical sites to upload their data. And actually, as you may expect, and we may have expected, the clinical partners upload the data that they had without any control on the quality of those data. So it happened that, for instance, in some cases we had also the complete examination of a patient, so not only prostate but also other exams, and also the quality of the data were not so high and as we were expecting. So what we started to do at a certain point, realizing this issue with the data, is to implement a quality control based on defined characteristics that the clinical coordinators has defined. And actually on the prostate, there are different studies that try to assess the quality of MRI images. One of these is the PI-QoL study. So according to this, we are implementing, first of all, the collection of clinicians' feedback on the quality of this data, and then we are moving to an automatic control of these characteristics. And after that, we are also acquiring some very basic quality check, which is about the signal to noise ratio and so on and so forth. But these are the very basic ones. So upon this, what we are doing is implementing a system that tells us whether the data are of quality or not. So actually, this is an important thing. And what we are supposed to collect are quality data, because at the end of the project, this data will be also shared and open to researchers, communities and innovation communities. So we need to be sure that the data are of good quality, and also for our models, of course.
Let's say I have a third and then last question. I don't know. There was a slide where you collected, where you show the results of an inquiry of radiologists about what they are willing to, what they want from the AI models, right? I don't know if it was inside this this big project or not. But I remember that there were only few tens of answers. I mean, there were like,
just because they are only within ProCancer, and so they are just 380. So sorry, 380. 38 replies. So just the few clinical partners within the consortium. So because it was just within ProCancer, and now we are circulating it to Oncology Imaging Association. And so we are expecting to collect maybe 380 replies in that case.
Okay, so in the first case, it was 38 partners, and all of them just had one answer. Each of them.
No, they are 30. They are 13 partners, clinical
13,
partners.
okay.
So we got more reply for them.
Okay. All right, because it's the same project problem, I guess, from the paucity of data. This is also an example of scarceness of data.
It is, but it is limited to the project currently now. So we are using this just for the project purposes, but the idea is to broaden, of course, the audience and then get hopefully many more replies.
Okay, all right. Yeah, from Vincenzo, do you have questions?
Yeah, I mean, I had a sort of general question actually to both. I saw somewhere, although I'm not by no way an expert in this area, specifically in the medicine applications. So there was an evaluation of performance of, let's say, diagnostic performance by physicians, assisted or not by AI tools or imaging tools such as these. I'm just wondering if you have any experience, or if maybe it's not just on within your scope, but let's say whether you have any experience in this sort of say after the fact, once you implement whatever whatever tool you use to analyze images and provide it to physicians, how do performances in diagnostic accuracy improve or change or not, or perhaps you have no experience?
Maybe I can say something. Not directly in diagnostic performance, but what we see is that we are, for instance, interested in the delineating of the tumor and brain MRI before the intervention, and if we give the physicians or the technical staff there and previous estimation of how the tumor, where the tumor is from automatic methods, then the time they need is drastically reduced. So from around 10 minutes to 1 minute. So they need just, because in most cases they just have to review, is it correct? And they're finished, yeah. And only in some cases they have to correct it. And before they had to delineate each slide. And so that's an appearance that you cannot, or that's my opinion, in most applications you cannot replace the physician, but you can assist to reduce the effort.
Also because the physician doesn't want to be replaced. I guess that's the problem, right?
They cannot be replaced. I mean, they cannot be replaced. Yeah. And of course, also in our case, I mean, we checked for the lung segmentation tools, the time that is requested to radiologists to estimate the lung involvement of the interstitial diseases. And of course, when you have an automated segmentation tool, it is quite easy. I mean, you just segment automatically the slice of the CT and you get the volume reconstructed. But in general, I mean, this is an assessment that we have done at research level. In ProCancer Eye, for instance, and I think also in other research projects, large research projects, what we are planning to do is that when validating the system, we need to verify, so the prediction system, which are meant to support the clinicians in diagnostic decision. In that case, we are going to assess the reading time of the case by clinicians when it is assisted or when it is not assisted by the system, and also, of course, the performance with and without. But this, of course, is still a side experiment that cannot be done in the clinical practice because I mean, these are still research products that cannot be used in the clinical practice by the radiologist. So what we are going to do is perform actually a trial, but it is an experimental trial to assess actually the utility and effectiveness of these tools to support radiologists in reading, in this case, prostate cancer MRI data. So this is at the end the final goal of this method, so they should be helpful. If they complicate the reading time, or I mean, they are not really useful to clinicians, I mean, they make no sense.
All right, I see that there are two questions asked from the audience. The first one is for Sara. Said actually they have this person Paolo Fazzini has two questions. The first one is in prostate cancer aggressiveness evaluation, do you make predictions on how the tumor will develop in time using AI? Let's start with this, then there is a second one.
Well, the aggressiveness that we predict is based on the histopathology results, so on the bioptical results. And in this case, it is assessed by the histopathologist by assigning what is called the Gleason score. So the Gleason score is a number that describes actually how cells of the tumors are differentiated. And so if the tumor is aggressive and may have a worse outcome, or if it is not so aggressive, let's say in this case the Gleason scoring low, and then one can decide whether to intervene or not. So the idea is of this aggressiveness prediction is to steer the intervention procedure. Then what happens in the case of the prostate is that when the clinical significance and so the aggressiveness of the tumor is very low, maybe the patient are put in active surveillance, and this is one of the use case that we are addressing in ProCancer. So distinguish when the patient should be included in active surveillance, so and be examined in a while, or whether he should go to a complete prostatectomy, so a chirurgic intervention.
Okay. Yes. So this is the evaluation of the aggressiveness in a certain moment. He asked if they
yes, of course, because at the end, I mean, we will have another examination, and then you can again verify whether there is a change in tumor appearance.
So you need another examination.
Of course, we can.
Okay, the second question he has is only if the answer to question 1 is yes. So if you make predictions about the development. Looking into the layers on the relevant slide, I didn't notice typical forecasting ANN tools such as RNN, LSTM, echo state networks, etc. Did you perhaps try them and found out they don't help?
Not just because we are not processing time series data, in this case imaging data in time. We just use one time point data to predict aggressiveness or to predict the possibility to include the patient in active surveillance, or to predict also recurrence of the tumor. So we just use one point time data. Okay.
Okay, right. He said, thank you, disregard question 2. He had already answered himself. Okay, and then they have Rabia Aziz. Hello, first of all, I would like to thank both speakers for wonderful presentations. My question is to Sara. Sorry, Jan. That the segmentation you presented is based on attention UNet. Did you try some other variants of UNet to perform segmentation?
Yes, as I said, maybe too quickly, we also tried the recursive UNet, so using also a recursive mechanism that provide a first segmentation, then use the segmentation to refine the initial one. And actually, this is a very heavy network to be trained, and we train it both with and without attention, without getting any real improvement. So in this case, it did not make sense to use too complicated network. And for instance, there is a very well-known state-of-the-art unit, which is NN unit, which actually is a very basic unit that is used to segment any type of medical imaging data. And what also the authors of this network claim is that usually you need to while engineering the data that you pass to the UNet network to get actually good and well acceptable results. So actually what we got testing these different versions of UNet is that, I mean, they are right. I mean, the UNet is a well-performing models, and just the addition of the attention module were enough for our purposes, and we obtain even a higher performance.
Okay, so maybe a general question for Jan. We saw from Sara that there are these big kind of projects that she presented, this cancer how is it called again? The Cancer AI? No, Cancer.
Pro-Cancer AI and
Pro-Cancer AI.
EHRHARDT.
Yeah. You presented first Pro-Cancer AI, and then you presented a project made of 5 parts, of which also not a project.
It's a kind of yeah, it's a network. Exactly.
A network where there are 5 kind of big studies put together in order to somehow cover a big part, a bigger part of the spectrum. So the question to Jan is, are you also part of such, let's say, bigger networks? And what do they do in your case?
Not directly, no. So there is a community in Germany. I was that was also my the reason why I sent my CV that late on a conference. And there's a German community in medical image processing knows this very well. So I know very well the authors of the NN unit project, for instance, and but we have not yet not a consortium in this way. Yeah, and I also I noticed on Sara's slide that there are few pins of partners in Germany to see. Yeah, so no, currently not. Yeah. There, so the group at our institute is quite large. We have more than 30 people there. So and most of the work was done within the group. So yeah. Okay. But the population analysis, maybe that is your question related to, because we do so much with population analysis, is because there is a large consortium called ADNI for the Alzheimer's disease data, and they provide many data sets for brain MRI images, and these data sets are used. And if you use this data, then you automatically are inside this consortium. So on the publications, the consortium is mentioned, and in this way, yes, but not in the sense you mean.
Okay. Because I guess that's the way too. I mean, I worked for a while in bioinformatics, and when there were microarrays, and yeah, and actually every study, because of difference in protocol, because of difference in technology, they were not comparable. I mean, so and obviously if this is the case, then the uptake will never be, so will never happen. But I guess that's the direction in which AI as a tool for medicine is going. I mean, it has necessarily to go, right, Sara? Yeah.
Yes, yes. But in the brain, there already have been a big initiative, which is the Brain Project, that tried to somehow standardize the acquisition, but also the analysis. So the brain is one of the most advanced field for medical imaging, but for research in general, let's say, in the biomedical domain.
And I guess that medical images is somehow even more robust and more, let's say, clearly considered in the medical practice than genetic profiling.
Well, genetic profile it is as well. I mean, it is a relevant part. It's expensive, let's say. So in many research projects, it's not easy to include that part, but it's taken in due consideration, I would say.
Okay. Right. So from my part, we are already at 12. We already past 12. So our time is actually over. But if you have a burning question or a burning comment, you can do it before we say bye bye. Vincenzo? No. Okay. Everybody is content with what we've got until now. So from my side, it was very informative and. Both presentations, and I thank you for them, and yeah, I thank the audience, the one who remained, because there is always this let's say exponential decay after a certain time.
Well, it's a flat tail. That's not really.
Yeah.
It goes down, but not quite exponentially.
Yeah. Okay. Yeah. Okay. And okay, so that was also, as I said, the last webinar of the series. I will send, as always, to all participants the slides, to all registered participants, not only the one who actually connected the slides, and the link to the YouTube video when we have it. And as I was asking the speakers, if something comes out of this webinar, of the webinars, in the sense of cooperations, of even common projects in the best cases, then please let me and Vincenzo know, because for us it's important to have this feedback. So from my side, thank you, and yeah, have a nice day.
Thank you.
Yeah.
Thank you.
Thank you.
Bye.
Thank you very much. Thank you for the invitation. Bye.
Goodbye.
Bye. Bye. Bye.